In this screencast, I want to show that two problems are NP complete. And the way we're going to do that is we're going to take 3SAT, which we know is NP complete, which, remember, that means that every problem in NP can be reduced to 3SAT, and that 3SAT is also in NP. So 3SAT is at least as hard as every problem in NP. And what we're going to do then now is show that independent set is in NP and that 3SAT can be reduced to it. So independent set is at least as hard as any problem in NP. And then we'll do vertex cover problem, and we'll reduce independent set to the vertex cover problem, which is also in NP. So it will be NP complete. So that's going to be the strategy. The big steps are going to be, the hard part will be reducing 3SAT to independent set, and then reducing independent set in polynomial time to vertex cover. So first let me define what I mean by the independent set problem. An independent set is a set of size m in a graph of the vertices. So we're going to have a subset of the vertices v prime. V prime is going to be size of m, and the big constraint is that for all vertices in the independent set, that none of them are adjacent with one another. So all the pairs of vertices in here are non-adjacent vertices. The independent set problem is going to be determined for a given graph and some positive integer m, whether G contains an independent set of that size m. So here's a graph, and the red vertices are an independent set. As you can see, there's no edge between those two vertices. Here's a larger independent set. In fact, this is a maximum independent set for this graph, and it contains 4 vertices in the independent set, and again, there's no edges between them. And then here are some more examples of independent sets. So you can see independent sets, a single vertex from a graph would be a trivial independent set of size 1, and basically in general what we'll be looking for is the largest one, but we'll just define a decision problem where we're looking for an independent set of size m. Okay, so recall that to show independent set problem is NP complete, we need to do two things. We need to show it's in NP, which means a potential solution can be verified in polynomial time, and we need to show that an NP complete problem can be reduced to independent set. This is going to be the hard part. This part I'll do right now. It's pretty easy to see that if you have a set of vertices, you can check whether it's independent set or not just by looping over the edges in the graph and making sure that at least one of the vertices of each edge is not in S. The time complexity of that way of doing, there are other ways to do it, but the time complexity of that way of doing is simply the cardinality of the edges times the cardinality of the set S. This is sort of a brute force approach, but we don't really need efficiency here. We're just trying to show, in fact, that independent set is in NP. The second step is the hard step. So we need to show that some NP complete problem can be reduced to independent set. We're going to choose 3SAT to do that. So we know that 3SAT is NP complete, and now what we have to do is show that it's polynomial reducible to independent set. So what we need is a mapping T from instances of 3SAT into the instances of independent set. So for every instance in 3SAT, so in other words, for every set of clauses like this in conjunctive normal form, we need to produce a graph and a problem statement for what the problem will be in independent set that corresponds to this set of clauses. So how do we do that? Well, for each of the xi's, for each of the unknown Boolean variables that we're trying to find values for to make this expression true, we're going to create two vertices, one corresponding to xi and one corresponding to xi bar, respectively. Okay, and so these correspond basically to the values of each of the possible Boolean variables in the expression. For each clause, okay, and this is just stands for some typical clause. These could be xk bar, etc. Basically what we do is we create edges connecting each pair of the vertices, basically making a triangle. So for example, if we look at this first clause here, x1 or x2 or x3, we're going to create this triangle with x1, okay, remember that's a vertex that we've created, x1, x2, and x3 bar. So for each of these clauses, we create a triangle. So I didn't have left off the end here, obviously. And then what we need to do is we need to make sure that only one of the xi and xi bar pair can be true. And so the way we'll do that is we'll have an edge between x2 and x2 bar. And this means that only one of those are going to be able to be in the independent set. Similarly, by making these triangles, only one of these vertices can be in the independent set. So you can see what we've done is we've created constraints in our graph that prevent any violation of what we need for this expression to be true. So in addition to that, if you stop and think about it, if I can find an independent set that's a size, the number of clauses, so suppose there's n clauses and I get an independent set of size n, then what's that going to mean? That's going to mean that only one of these vertices can be say in this triangle, can be in the independent set. And so if we have an independent set of size n, that means that at least one vertex from the independent set will have to be in in each triangle. That, along with these constraints, basically will guarantee that the Boolean expression is true. So let's go on to the next slide and prove that. So given an instance of 3sat with n clauses, an independent set of size n in the corresponding graph corresponds to a satisfying assignment to the 3sat problem. Okay, the proof. There can be at most one vertex from each triangle, right, in the independent set. Thus, there must be exactly one vertex in each of the n triangles. Set the value of the corresponding logical variable to true or false, depending on if the vertex corresponds to an xi or an xi bar. Okay? This makes each corresponding clause in the 3sat problem true, and thus is a satisfying assignment for the entire expression. Given the independent set, this can be done in linear time in the number of clauses of n. So remember how this idea works. By solving the independent set problem, we basically transform it back into a solution for 3sat. So if we have a black box that solves independent set, and this construction takes polynomial time to take 3sat and construct the graph, and then solve it with the black box, and then polynomial time back to the 3sat problem, we will have shown that if we can solve independent set in polynomial time, then we can also solve 3sat in polynomial time. Thus, 3sat is polynomial reducible to independent set. This is one of the things that makes working with NP-complete problems so interesting and so important, is that we've taken a problem in Boolean logic and we've transformed it into a problem in graphs and shown that in some sense they're equally hard to each other. Thus, the problem, even though problems are in different domains, it's pretty amazing that we've been able to show that they're of equal difficulty and that solving one allows us to solve the other. This is an important insight we get from studying NP completeness. So now I want to take a quick look at a simpler example where both the problems are graph problems. The other problem we're going to talk about is the vertex cover problem. So what's a vertex cover? A vertex cover is, in some sense, and you'll see exactly what I mean by that in a second, it's sort of the opposite of independent set. A minimum vertex cover is a set of vertices so that every edge is covered. In other words, you take any edge out of the graph, and at least one of its vertices will be in a vertex cover, in the vertex cover. And just like we look for a maximum independent set in general, we normally would be looking for a minimum vertex cover. But again, we'll just focus on the decision problem for vertex cover, which is to find a vertex cover of a given size. So again, to show vertex cover is NP complete, we need to show that vertex cover is NP, and we need to show that an NP complete problem can be polynomial reduced to vertex cover problem. So we'll do that. Again, it's typically easy to do, show that the problem is NP. Given some candidate solution to vertex cover, can it be verified in polynomial time? And the answer is yes. Just verify that at least one of its vertices are in the proposed vertex cover, cover every edge. So for each edge, verify that at least one of its vertices in the vertex cover. Again, this can be done in big O of the cardinality of the edges times the cardinality of the set. Just loop over the edges and check to see if one of their vertices is in S. All right, so now the hard part is going to be, let's reduce an NP complete problem to vertex cover. We're going to use independent set, and you're going to see that this one's pretty easy. We're going to show that independent set can be polynomial reduced to vertex cover. So here we go. Our mapping is going to be take an instance of independent set, create an instance of vertex cover. And that mapping is just the identity map. So all we do is make a copy of the graph. That's clearly big O of E, the cardinality of the edges plus the cardinality of the vertices time. So to find the independent set, S in G, okay, so we'll take the graph over here, map it to the graph over here, same graph, and then what we'll do is we'll take the vertex cover of some size. So if we're looking for an independent set of size k, we'll look for a vertex cover of size the cardinality of v minus k. In other words, we're going to basically look at complements. So, and then we'll take S to be the complement of the vertex cover. And we claim that S is an independent set of size k. That's a typo. So suppose S is not an independent set, then there must exist an edge, VW, such that V and W are both in S. And that's, remember what S is, it's the vertices minus C, it's the complement of C. So that implies that V and W are both not in C. But that implies that C is not a vertex cover because there's an edge VW. So by contradiction, this implies that S must be an independent set if C is a vertex cover. So in this screencast, we've looked at two problems. One, first one, where we reduced 3-sat to independent set, was more complex, but it showed the linkage between a problem in Boolean logic and a problem in graph theory. And the second problem just linked two problems in graph theory. These are sort of representative in some sense of the types of problems you run into when you're trying to show that something's NP complete.